The overflow flag. The overflow flag, as opposed to the carry flag, understands signed addition and subtraction. I remind you that the carry flag that we spoke about earlier understands unsigned addition and subtraction. It is only reasonable that we should have some kind of flag that actually can understand signed addition and subtraction. I just want to remind you that we are talking about the 2's complement representation here. Let's talk about addition. The overflow flag is set if the addition of two positive numbers has a negative result. It is also set if the addition of two negative numbers has a positive result. Think about it for a moment. If you add two positive numbers and you have a negative result, obviously something went wrong. Because we know that in the natural case, when we are outside of our computer, the addition of two positive numbers should result in a positive number. Also, the addition of two negative numbers should result in a negative number, in a negative result. Some examples about subtraction. The overflow flag is set if we try to do something like this, positive minus negative, and we get a negative result. Why is that? Because we expect that positive minus negative is like positive plus positive, and it should have a positive result, not a negative result. The same goes for negative minus positive. If negative minus positive has a positive result, then the overflow flag is going to be set. That is because negative minus positive actually equivalent to negative plus negative, which should have a negative result, not a positive result. The overflow flag has the special role of telling you if something went wrong with your signed arithmetic calculation. If you did some kind of arithmetic calculation which considers the sign as important, or which is actually signed, then the overflow flag is going to tell you if something went wrong, if you have some kind of unexpected result. How does it actually work? The processor looks on the most significant bits of the two operands and the most significant bit of the result. I just remind you this notation. MSB actually means the most significant bit of the number. Maybe it could be easier for you to understand it as the leftmost bit of the number, including the leading zeros, of course. If the result of the addition or subtraction has a reasonable sign, the overflow flag is clear. If it has an unreasonable sign, the overflow flag is set. Just a comment about it. Positive plus negative can never set the overflow flag. Why is that? Because there is no reasonable prediction in this case. The result could be both positive or negative. So actually, the processor really tells you that you are on your own in this case. The processor can only help you predict what reasonable result should happen in the cases of positive plus positive or negative plus negative. It cannot help you in this case of positive plus negative because it cannot actually predict the reasonable result. The same goes for positive minus positive or negative minus negative, because positive minus positive could result both in positive result or negative result. Also, negative minus negative could be positive or negative. There is no reasonable prediction in this case. As an addition, if you ever want to clear the overflow flag, you can just do something like this. Add a positive number and a negative number. This is not the optimal and cleanest way to clear the overflow flag, but it will work. Positive plus negative is always going to clear the overflow flag. Let's look at an example, or maybe even some examples. Here we have those three instructions, 2 moves and 1 add. The first move sets AL to be the value 7F, which is probably the highest positive value that you can have inside AL. And CL contains 1. Finally, we add CL to AL. The result is going to be 80 in base 16. And the overflow flag is going to be set. Why is that? We can see that we had those two positive numbers. 7F is positive and also 1 is positive. And the result that we got is 18. And 18 is negative. Why is it negative? Because the highest bit of 80 is 1. The sign bit of 80 is 1 in the 2's complement representation. Therefore, the overflow flag is going to be set. Let's look at how it looks like. We have those two numbers, 7F and 1. Represented in binary, we have it this way. Each of those numbers is of size 8 bits. 7F is the highest possible positive number that fits inside 8 bits. Now that we add those two numbers, the result is this number, 1 followed by 7 zeros. If we take a look at the most significant bits of those three numbers, we can see that the first two numbers, 7F and 1, are positive because the most significant bit is 0. In the 2's complement representation, this means that those two numbers are positive. The resulting number, 80, has a most significant bit of 1, which means that it is negative in the 2's complement representation. So we have some kind of unreasonable result. The result of adding two positive numbers is a negative number, which is a bit strange. That is why the overflow flag is set here. Let's look at some more examples. In this example, we store the value 7 and then 7Fs, which is, I remind you, the highest possible positive number of size 32 bits inside EAX. We also store the number 1 inside EDX, and then we add those two numbers. This is somehow pretty similar to the example we've just seen. Okay, let's take a look at it for a moment. In this example, we added 7F and 1. And in this example, we add 7 followed by 7Fs with the number 1. Again, we have a result of 8 followed by 7 zeros, which is pretty much similar to the result we got earlier of 80. And again, the overflow flag is set here. It is set because we added two positive numbers. This number is positive, and also this one is positive, and the result is negative. You can see that the most significant bit of this number is 0. The most significant bit of this number is also 0. However, surprisingly, the most significant bit of this number is 1. Regarding the 2's complement representation idea, we actually added two positive numbers and we got a negative number. That is why the overflow flag is set. Let's look at a contrasting example. Here we subtract those two numbers. We have this number 7 followed by 7Fs, and again the same number as before, 1 stored inside EDX, and then we subtract those two numbers, 7 followed by 7Fs, we subtract 1 from this number, and the resulting number is this number, 7, then 6Fs, and then E. This time the overflow flag is cleared. Why is that? We subtracted positive minus positive. I remind you that this is one of the cases in which the processor cannot predict the reasonable answer, because positive minus positive can actually result both in positive result or negative result, both of which are going to clear the overflow flag, because both of which are reasonable. So this time the overflow flag is clear. We have positive minus positive equals positive. Let's take a look at another example. Here we store this number 6342 in base 16 into dx. I remind you that dx is of size 16 bits. Then we store this number 2 followed by 30 inside cx, and we add those two numbers. The resulting number is 8342 in base 16. And this time the overflow flag is set. Why is it set? Because we added two positive numbers. This number is positive, and also this number is positive. I remind you that those two numbers are positive regarding the 2's complement representation. That is because their most significant bit is 0. However, the result begins with 8, which means that the most significant bit of this number is going to be 1. So this number, regarding the 2's complement representation, is negative. So we have positive plus positive equals negative. That's why the overflow flag is set, because this is not a reasonable result in this case. Another example. We store the value of 8 times f inside ESI, and we store the same value inside EDI. I want to remind you what this value represents. This value is actually minus 1 in the 2's complement representation. Finally, we add those two numbers, and we get this number. I want to remind you that in the 2's complement representation, this result actually means minus 2, which is all reasonable. Minus 1 plus minus 1 is minus 2. In this example, the overflow flag is going to be clear. Let's try to understand why is that. We added two numbers. Those two numbers were actually the same. Both of those numbers are made of 8 f's. The first number, which we store inside ESI, is a negative number. It is a negative number in the 2's complement because the most significant bit is 1. The same goes for EDI. So actually we add two negative numbers. The resulting number inside ESI, which is minus 2, is also negative. It is negative because the highest bit, the most significant bit, is 1. So we have here negative plus negative equals negative, which is pretty reasonable. That is why the overflow flag is cleared. So just as a summary for those examples, whenever the result is not reasonable, the overflow flag is set. Whenever the result is reasonable, the overflow flag is cleared. Let's just remind ourselves as a summary what we have seen inside those examples. Here we have positive plus positive equals negative. That's why the overflow flag is set. In the next example, we have positive minus positive equals positive, which is reasonable. Therefore, the overflow flag is cleared. In the next example, we have positive plus positive equals negative, which is not reasonable. Therefore, the overflow flag is set. In the last example, we had negative plus negative equals negative, which is reasonable. Therefore, the overflow flag is clear.